Okay, hello guys, how are you? Good evening. Okay, so now we're going to proceed with part 2 of the video. So yesterday we were busy with work, energy and power. Okay, so we're still on work. So now we explored this formula where we had, you remember when we had that F net is equals to work net is equals to F net plus the displacement and a cos theta, and we also discussed basically this theta represents the direction, you remember, eh? Okay, so now we're going to do what we call the work energy theorem. So today we're going to focus on the work energy. We're going to focus on the work energy theorem. So now, based on what we did yesterday, we're gonna just extend a bit. Okay, so let's say, so now the work energy theorem. So if I can just say, let me just draw a situation first. So let's say we have a situation, we have a block with a mass of m. So it's very important to understand, guys, when you talk about the force, let's say we apply a force on this block. We say F net is equals to the F applied, provided this force is constant force. We are just exerting a constant force on this block. So this block, it started moving from here, from this position to this position. We know that if it moves from this position to this position, we represent our displacement as x. Okay, then it means now the block will be here. This block will be here. Still, this is the force applied today. Okay, so now if we pull this block with a force, with a constant force, when they say constant force, it simply means the force that you're pulling does not change. It's just constant. If your force is 50 Newton, you're pulling it with 50 Newton throughout this displacement. Okay, so now when we talk about the energy theorem, we say the work energy theorem, basically we are representing the work net in terms of the kinetic energy, because of whenever we talk about energy, when we talk about energy, basically it means we must relate this thing with any energy that we have. So we can relate it with either kinetic energy or potential energy. So now, as we can see that this thing is just moving horizontally, so the height is the same. So basically we can say that the potential energy is 0. So let's say this thing starts from the initial velocity, then here it gets to Vf. Our initial velocity is going to be vi, and this one is going to be our final velocity traveling at the x distance. Then it goes a displacement of x, and then we also have another thing which is very important, which is the acceleration. So it means this thing is acceleration, it's also accelerating this way. Okay, so now we want to derive the equation, the work energy theorem. So now, since this thing it is pulled by a force, then in terms of we are going to represent this thing in terms of Newton's second law. So if we check Newton's second law here, if we check Newton's second law, we have that from the Newton's second law, we have that F net is equals to mass times acceleration. Okay, then what do we have from here? Then from here we can just say F net is equals to mass times acceleration. Therefore we can say, basically, make A the subject of the formula. Is going to be F net is divided by mass. We can say this one is our first equation. We got this formula from Newton's second law. we know when you're dealing with Newton's second law, whenever you think of Newton's second law, or F net is equals to mass times acceleration, then if I divide both sides by m, I get acceleration is equals to the F net, that constant force, divided by the mass. Okay, so now we use, since now we what we do is we make our acceleration to be constant. So let's say this acceleration is constant. So if this acceleration is constant, we can use the equations of motions. You can use equation of motions. So I need to choose a relevant equation of motion that I'm going to use, that is going to make sure that at the end of the day I match. So which equation can we use? So obvious, there's only one equation of motion in time. So it means we're going to have Vf squared is equals to Vi squared plus 2. What we have 2, then acceleration, then multiply by our displacement. This is the equation of motion. Then we can simply say this one is the second equation. Label. This one is the second equation. So we have two equations. So we can solve these equations simultaneous. So I can substitute from here. I can just sub equation 1 into 2. Label. So basically when I substitute equation 1 into equation 2, what do I have? Gobale Vf squared is equals to Vi squared plus 2. Then what will be my A? My A, salvalor A is F net. Is F net divided by mass. So robale F net divided by mass. Then we have also our delta X here. Then we can now solve this equation. So our goal now is to solve this equation further. So now from this equation, we have an equation of motion and then also the Newton's second law question. Okay, so now we're going to solve this thing. So we are trying to derive the work energy theorem formula. So from here we just solve. I can multiply, since it's an equation and then mass is divided by mass, I can multiply by mass the whole of this equation. So okay, so I can only, okay, let me take this V initial this side. So I'm going to have Vf squared minus V initial squared is equals to 2 F net divided by mass, then delta X. Then I can also, then from this equation, I can multiply by mass. I can multiply the whole equation by mass. Robale M Vf squared minus M Vi squared. Then when I multiply by mass here, the mass yotuha rabale 2 F net multiplied by delta X. Level. Then I can divide everything here by 2. I can divide everything by 2. I can divide everything by 2. I can divide everything by 2. Then when I divide everything by 2, basically this one is the same as 1 over 2 mv f squared minus 1 over 2 mvi squared. Then it becomes f net multiplied by delta x. So when we have something like this, what do you see? So basically the work energy theorem, it was derived by the what? It was derived by the Newton's second law and then also the equation of motion. Then from here, what do we notice? We notice, half mv squared f minus half mv squared initial. This is change in EK. What is f net multiplied by x? Basically, this one is equals to the work net. So now this is just how we derive the work energy theorem. So basically, what do we say? The net work done. So now it gives us the work energy theorem. The net work done on the object. can have this, that the work done on the object is what? Is equal to the what? To the change in kinetic energy of the object. So in a formula, Hegikwala in the formula is going to be something like this. So we're going to have something like, we're going to have like work net is equals to change in EK. This is the work energy theorem. So basically that's how we derive the work energy theorem. So how are we going to use this formula? So our question more examine it like different ways. So when you have a question along velocities and everything, I can be able to integrate between the work energy theorem and then that normal formula, work net is equals to F net multiplied by what? By X. This is what we have. Okay, let's take an example. I want us to just take an example. So by now, what do we have? We have explored this formula. We know this formula from the previous video. We studied that F net is equals to delta X, then cos of theta. We also learned this formula that work net is equals to the change in EK. So now these two formulas, they're going to help you a lot. They're going to help you a lot when solving problems. You just have to know what am I given. The question about feeling so for example, let me take this example. Let me just give you this example. So let's say we have a question and then we have a block here. And then this block is pulled by a force of 50 Newton with a displacement here, X, which is 6 meters. It is pulled for 6 meters from point O up until point P. We have point O up until point P. It is pulled like this. And then now what they give you is that a worker pulls a crate, and then this is, let's say this is 30 kg. This is 30 kg. Okay. He pulls this thing on the floor at a constant force. Ne? Then we have a frictional force. They also tell us that we have a frictional force. A frictional force of how much? Of 30 newtons. I guess. So it's very important to understand the grade grade 11. Grade 11, Newton's second laws, they are very important because of they are integrated with just work. So it's very important. And then you also need to understand friction is not always in the opposite direction with the applied force. But friction, it opposes the motion. And then another thing that you need to understand is that the displacement, it is always created in the direction where the object is going. So if the object is going to the right, the displacement will be created where? To the right. And then another important thing here about this question, make sure before you start attempting any problem, choose direction. Let me say I'm choosing to the right to be positive. It means if I get any answer that is positive, I know it's to the right. If I get answers that are, when I'm dealing with vectors and I get answer that is negative, I know it's going to be to the left. Okay. So now the first question, they want me to draw a free body diagram. Yeah, they want me to draw a free body diagram. Okay. So now let me draw a free body diagram. It's very important to draw a free body diagram. Okay. So a free body diagram, it's how we draw no tomaga dot. Like you can't get this thing wrong. A free body diagram, a dot, you start with the dot. Like ka dot. Then you just represent the forces that are here. We have the applied force. Then we have the what? The frictional force. And then the frictional force cannot be more than the applied force. Right? Then we have the normal force, and then we also have the what? The gravitational force. It's 4 marks. It's a free body diagram. This is our free body diagram there. Okay. Then they said, now calculate the net work done when this thing reaches P. You see, now we want to calculate the net work done when this thing reaches P. You see, I'm not given any velocities and everything. I know I'm going to use the normal work net is equals to F net. That one almost again, because I'm not given any speed, any velocities here. I'm given the displacement. Yes, I know all the forces. Yes, I can use this formula. You just need to know how to integrate this thing. We have this thing. We know now. Oh, I can use this formula. One, we have two formulas. So two. How can I check out these formulas? They are working. Work net. So you can also equate them to each other to solve any problem. So now they want us to calculate the net work done. So if we want to calculate the net work done, we want to calculate work net. So we know that work net is going to be F net multiplied by delta X, then cos of what? The cos of theta. We know that if we want to calculate the work net, we need F net. And it's very important, guys, that when you're calculating F net, you take note of the direction. F net is going to be, this one is going, 50 Newton is going to the right. So it's going to be 50 plus, because when you say F net, you are adding them. But this one is going to in the negative direction. So it's going to be minus 30. So it means your work net, your F net is going to be what? Your F net is going to be 20 Newtons. Please, guys, do not confuse work net and F net. Substitute the F net and work net. Do not confuse them, guys. You confuse them, you are child. You confuse them, you are child. Like you are a child. Serious. And then we are not going to bail anybody out if you lose this information. This is very important. Okay, so now it's a matter of substituting. Okay, now let's substitute. We got our F net as 20. Our displacement here. How can I check that F net is positive? If F net is positive, it means our F net is going to the right. It means the object is going to the right, because we got F net which is positive. That's what I'm saying. Now the F net is going in the same direction as the displacement. So they're going to form. So our displacement here is 60. Then cos of theta. You said theta can be 0, can be 90 or 180. But since the F net is going in the same direction as the displacement, they're going to form 0 degrees. Clever? Then what are we going to have? Then we're going to say 20 multiplied by 6. Then 20 multiplied by 6 is 120 joules. This is our F net. This is our F net. Now let us spice up this equation now. Let us spice up this equation. Okay. So now we can say, let's say for example, on the very same question here, I'm just going to fold this thing. So that we can be able to see the question. So I want us to, we are still busy on this question. So now what they say, you remember the statement, Hore? Using work energy theorem. Now they're asking us, using the work energy theorem, calculate the velocity of the crate the moment it reaches point P. We want to calculate the velocity of the crate the moment it reaches point P. So we said now, the initial arena, they said this thing is started from rest. So we want to know what will be our final velocity. So I told, the velocity and everything. You cannot use this F net is because but we know how we have to use energy principles. So they know the formula the work energy theorem. Then work energy theorem work net is equals to the change in what? Work net is equals to the change in EK. Okay, then the work net is equals to the change in EK. Then what we have, EK is equals to half mv f squared minus 1 over 2 m half mvi squared. That's what I'm saying. Then we already You can recall that from the previous, we already calculated work net already. I have a work net. F net is equals to delta x cos theta. Now my work net here is going to be 120. So I substituted my work net as 120. Then we have 1 over 2. My mass is 30 degrees. Then a VF is the one that I'm looking for, minus 1 over 2, 30, and then V initial. It's very important that you also substitute. Obvious, when I'm going to substitute here, it's going to be 0. Why? 0 fail. But it's very important, guys, because physics, the way KEPS curriculum they give you mark for writing down the formula. They also give you marks for substituting into the formula. So it's very important that already here you have a lot of marks. If it's 5 marks, already you have a lot of marks by just substituting. We cannot substitute was create the answer, but we have a lot of marks. So more, we are not only just marking the final answer. The final, if the question A get 5 marks, if the quiz question get 5 marks, the final answer autogra elorke 1 mark. So go once we are not marking the final answer, but everything must be pashash. So now we have 120 is equals to this one. What do we have? We have 15 VF squared minus, then this one becomes 0. You see now. Then we can divide both sides by 15. We can divide both sides by 15. Then we have our VF to be how much? Then we can solve our VF. We can solve our VF. We can solve our VF. Where's my calculator? Okay, where's that calculator? Okay, so now we can solve our VF to be 120 divided by 15, the square root of 8, which is going to be now the square root of 8. So we get our sorry guys for the network, you know. Kunzima bafethu, kuzima 2,883 meters per second. This one is our final velocity. This one is going to be our final velocity. You see, guys, ne? This is the work energy theorem. Okay, so now I'm going to do the last thing. So I want to discuss these formulas, and then at the end, tomorrow I'm going to do just questions. So let us discuss these formulas so that you have them. And then tomorrow what I'm going to do is I'm going to just show you how to treat different formulas. Okay, so there's something that is very interesting here, guys. It's very interesting, which we call the conservative and non-conservative forces. This is something they struggle understanding. Most people will struggle to understand the between the work done, the conservative force and non-conservative forces. So now I just want to quickly discuss the conservative and non-conservative forces. Okay, so we're going to discuss conservative and non-conservative. So basically, when conservative and non-conservative forces are present. So when you talk about conservative forces, we say the work done by a conservative force depends on the initial and final position. So the work done by a conservative force depends on the initial and the what and the final position. So basically we say this one we can say, and it's independent of pathway. So basically we can say it's path independent when you talk about a conservative force. Let me specify here. I'm talking about a conservative force. I'm talking about a conservative. When I'm talking about a conservative force, so a conservative force is work done. So basically the work done of a conservative force depends on the initial and the final position. So when you talk about conservative forces, we can represent conservative force by Fc. So basically conservative forces, we can say they are non-wasteful forces. Basically they are internal forces. We talk about internal forces. For example, let me discuss this one. One example of a conservative force is gravity. Gravity. Gravity is a non-conservative force. It's not a conservative force. It's path independent. It does not depend on the path. So I just want us to take one, for example, RT ball. We're going to put the same ground. We're going to take an incline here. So we take these two things. We put them under the same height. I'm going to take these two things and then I'm going to put them under the same height. This one is on an inclined plane. Obvious. When it's on the inclined plane, this one, we put them under the same height. So this is the ball. So we have the ball. So we put them under the same height. So they are under the same height. Again, so a conservative force, it depends only on the initial and the final. So it's independent. I depend more pathy. When I calculate the work done, bolo e roller on an incline, le bolo e kenwe dropper, I must get the same work. Okay, so I want us to prove that thing. I want us to prove it. So let's take this one. Let's take this one. So this one, what we have, when I just throw this thing is going to go downwards. You see? Where? So the force that is acting here is Fg. Fg is going down. So here you got the work done by Fg. Work done by Fg for the first one, is going to be Fg multiplied by x cos of theta. So my Fg is basically mg. And then my x, since it's going down and they're going in the same position, they're going to be h. Then cos of 0. So basically when that work done by Fg here is going to be just mg h. So the work done here is going to be what? mgh. So now let's check the work done. The work done mgh. It means lemo like a roller on an incline. It must give me mgh to once or this thing is starting lemo the same position, even if the same position. So we must get the same work. Okay? Because we say this thing that are independent of the path. It means they don't depend on the path. So okay, now let me check the work done by this one. Obvious. If it goes like this on an incline, we have Fg parallel. So if it goes like this on an incline, we have what? We have Fg parallel. So Fg parallel, you a certain distance. We can call this distance d. And then this is a right angle triangle. Level. So since this one is a right angle triangle, it means this is also my h. Level. So it means now this one, according to our Fg, we're going to have work done by Fg parallel is equals to basically Fg parallel multiplied by d, because it's going to h d, because it's rolling at this direction. I get it's going down the incline. Level. Then what is my Fg? So guys, let me write this thing down. Let me write it here. So we have work done by FG parallel is equals to FG parallel multiplied by D. Level. Basically, D ke bolelang ka yona ke D a rolang. Level. So basically, FG parallel y2 hore ke mg sine of theta multiplied by D. Then we need to get this D. So D equal Salbala guys, this is for number 1. This is for number 1, and then this is for number 2. Now I'm doing for number 2. So now I'm doing for number 2. So now D equal I get it it's a right angle triangle. So I want to represent D in terms of theta and H. Let me just scribble it more citing. Sine of theta. If we relate trigonometry, sine of theta is equals to opposite. Opposite is H divided by hypotenuse. Then if I solve for D, I'm going to cross multiply. D is equals to H divided by sine of theta. H divided by sine of theta. And then this multiplied by D. I get mg sine theta. So robale mg sine of theta multiplied by D, which is just H over sine of theta. Sine theta cancels. So salang mgh. So when he throw a bolo mo imboto this thing, he throw a bolo situation 1, so then leggy roller, I'm still going to get the same work. Level work done here more, yeah, situation 1, work done here situation 2 is the same. So since work done here this thing is the same, if when I throw this ball, kisa kotlas, the work done, we can say initial is going to be mgh. Is going to be mgh initial. If I take it from the same height, from this height, then hekisa kodimo, hekisa from motas, kisa ko the same height, we can say it's m kvf. So it's also going to be mgh. So but it's going to be negative because it's going up, but fg is going down. So we can get from here, we can derive a work done by a conservative force. So we can say now a work done by a conservative force is equals to minus the change in EP. So another formula that we can use, that the work done by a conservative force is going to be change in what? Because it is just the change. The same. Engwe over positive, engwe yaba negative. So if you can derive this thing, the work done by a conservative force scale is independent of the path. It's going to be change in EP minus the change in what? In EP. So that is the work done by a conservative force. Okay. So I hope guys I haven't lost you. So now this is the work done by a conservative force. So now let's check the work done by a non-conservative force. Non-conservative force. Okay, so I will only discuss the non-conservative force. So non-conservative force, we have wasteful forces. It's basically the opposite of a conservative force. So we have 1, we have friction. 2, we have air resistance. And then 3, we have push or pull. Normal force, applied force, push or pull can be applied force, can be everything. Okay, so let me just stop the video here for now. You can go through everything that you have done, pause the video, rewind the video. This video also will be available on YouTube. I will also upload it on YouTube. You can also get it and share with other people. So okay, I think now I'm done for tonight. Then tomorrow we'll discuss, I will state the time. We'll discuss the non-conservative force and also derive the formulas that we can use, and we'll deal with questions afterwards. Okay, so now turn to it. What are non-conservative forces, right? Or our non-conservative force. So you can go through this thing, check your textbook, and then read through. Then after that, tomorrow we'll discuss them again, and then we'll go through examples. If you have any questions as you are practicing there, and you have questions that you are struggling with, you can also post them so that I discuss them further. Okay guys, thank you. Have a wonderful night. Have a wonderful night, guys. Bye bye. Tomorrow.